Hello everyone. This video is going to be about DMA in STM32. First, we will give out a general description to what's a DMA. Then we will get into the specifics of how to use DMA in STM32. And we will be going through the official ST documentation to really learn about DMA and how to use it in STM32. And as usual, the board I'm going to be using for this tutorial is the blue pill. This video is going to be a two-parters. This part we will talk about some stuff about the DMA, while I will leave some of the stuff for the other part. So stick around for the other part, and without any further ado, let's get right in the video. And let's start strong by defining what's a DMA. DMA simply is a coprocessor that works next to the microcontroller's core. It can only do one operation, move data from a memory location to another memory location. And in ARM architecture, all peripherals are mapped to a memory location, which means that the DMA can also perform peripheral to memory transfers and vice versa, and some rare occasions can perform peripheral to peripheral transfers. The DMA performs its job without interrupting the Cortex-M core. It only requires some configurations at the beginning, but then can operate completely separate from the core. This allows for real-time applications to be possible because now you can, for example, pull data from a sensor into your microcontroller without involving the core of the microcontroller. So basically, it turns most blocking operations to a non-blocking operation. DMAs are usually structured in most microcontrollers as such. You have the DMA connected to the memory and also connected to the peripherals. The peripherals is then connected to the DMA through some request lines. And request lines can enable a transaction. But from memory to memory transfer, you can actually enable the transaction from your code itself. The DMA also has another port, which is a programmable port that is connected to the microcontroller's core. Through this port, the DMA acts as a slave while the core acts as a master. This port is used to configure the DMA on start. Now let's get to the STM32 specifics. There is some missing information from this diagram to fully understand how to use DMA in STM32. First of all, what happens between this and this? How transactions are handled internally inside the DMA. Also how the DMA prioritizes requests, and also how to configure the DMA from the programmable port. STM32 has 3 different implementations for the DMA scattered across multiple families. I have grouped all of the similar implementations into groups of A and B and C. These namings are not ST official. I'm just using it to be easier to explain in a video. We will start off by group A, and this is the bus matrix for STM32 F103 family of microcontrollers. We can see here that the Cortex-M3 is right next to 2 DMAs. Each one is connected to the bus matrix through a master port. Unlike other implementations, when we get to it, you can see that the DMA may be connected to multiple master ports on the bus matrix. And this is really the main takeaway we want to take from this diagram, is that each DMA is connected through only one master bus, or one master port to the bus matrix. Now, the bus matrix employs some kind of scheduling through something called a round-robin algorithm to ensure all of these masters can access peripherals without any problem. I'm not going to get into the specifics of this in this video, because simply it's not much details are stated in the reference manuals, and also it doesn't make that much difference when using the DMAs. Unfortunately, I couldn't find a diagram similar to the previous one for group B, but we could say that both of them has the same architecture, with the difference that each DMA has 2 ports on the bus matrix, hence called a dual port DMA. Port 1 is usually a memory port and port 2 is a peripheral port. Now this differs as well from a family to family, but generally speaking we can say that group A has only 1 master port on the bus matrix, while group B has 2 master ports on the bus matrix. Now let's crack inside the DMA and see what's happening really inside. This diagram is not official from ST. I have improvised this diagram from another diagram and from some information inside the reference manuals. while this diagram is official from ST. And we can see here that transactions are represented inside the DMA using something called channels. So a channel is basically a set of registers inside the DMA that hold some key information about each transaction. So for example, the memory location, the peripheral address, stuff like this, the direction of the transaction, whether it's from memory to peripheral, is it a memory to memory transfer, and stuff like this. We can also see here that both source and destination are connected to one AHP bus master, as we have explained in the previous slides. The arbiter is responsible for handling priorities of requests. It has 4 different settable priorities, low, medium, high, and very high. And you can set this through an internal register. When we get to the datasheet and the reference manuals, we will see this register. Now, here comes the difference between these two groups. We can see here that each request is connected through multiple peripherals, and all of these peripherals are ORed together. This introduces many problems because now you cannot have multiple peripherals connected to the same channel. As you can see here, ADC1, for example, is not connected to any other channel other than channel 1. Because if so, when you're enabling ADC1, it's going to enable multiple channel because it's an OR gate. And this adds some level of inflexibility when you are setting up DMA with peripherals for group A. And this is the main takeaway from these diagrams. Okay, so this is the next diagram. Both of these diagrams are official from ST, this one and this one. And we can notice that the first difference is the change of terminology. As you can see here, is that a channel now is called a stream, and the channel is repurposed to refer to something else. A channel now refers to each request inside a request line. So we have multiple peripherals connected to a request line. These peripheral lines are called A channels. So this is the second difference, the change of terminologies. The third difference is that now this group of microcontrollers add another level of control, which is which channel you want to activate this request or this stream. And this channel selector sits right here. When we go back to the other implementation, sits right here. Instead of this OR gate in group A implementation, group B you have a channel selector, which means that you can actually specify which peripheral you want to activate this channel. This allows ST's engineers to have multiple peripherals connected to multiple channels. So ADC1, rather than connected to only channel 1, can be connected to channel 2, channel 4, channel 7, multiple channels. And we will get to these mappings in the other video that we are going to get into the specifics of group B. Also, this group of implementation has something called a FIFO buffer. FIFO is short for first in, first out. And basically imagine a pipe, okay? You are feeding bits from one side of the pipe. Eventually, you are going to fill out the pipe, and the first bit that you have entered from this side is going to come out from the other side. So this is basically a first in, first out buffer. The first in, first out buffer allows for stuff like burst mode, double buffering, and true data conversion. And we will get to these in a moment and in the other video. So these are 4 differences. The first one is that group B implements dual port AHP masters, while group A implements only one AHP master. Group B has a channel selector, while group A has just ORs all of the peripherals together. Group B has a FIFO buffer, which allows for features like burst mode, double buffering, and data conversion. And the last thing, of course, I didn't write it because it's not that important, which is the change of terminology. What about group C? Group C has the same implementation as Group A, but both of the DMAs are connected through something called a DMA mux. A DMA mux is basically a multiplexer that takes all of the peripherals request lines and programmatically map them into whether DMA1 and DMA2 to whatever channel you want. And this is going to be the maximum level of flexibility out of all of the other implementations. Okay, so let's dive deep into the reference manual for STM32F1 group of microcontrollers. And let's navigate down to the DMA section. As you can see here, I have prepared everything. Man, we're going to have a lot of fun here. Okay, so let's see what data we have missed, what information we have missed, and what is new. So this is already information we know. DMA controllers are two, DMA1 and DMA2. DMA1 has 7 channels and DMA2 has 5 channels. Okay, so group A of microcontrollers has data conversion, supports data conversion, but it emulates packing and unpacking. So it's not true data conversion. Supports circular mode. This is something that we didn't mention. The DMA can also fire interrupts to the core of the microcontroller. And it does this through 3 events: the half transfer, a complete transfer, and a transfer error. The DMA performs its transfers through 3 phases. The first phase is loading data from the peripheral data register or the location that you have specified, depending on the direction. Then stores the loaded data into the other location. Then it decrements a register called the number of data transfers. And this is a very important detail, because what does this mean is that we can have multiple transfers firing from one request from a peripheral. So you can have multiple transfers inside a transaction. And the number of transfers are represented in this register: DMA, CND, TR. And the X, of course, represents the number of channels. Another thing the DMA can do is increment the peripheral address or the memory address. So let's just say we have 2 memory locations, okay? And when we set increment memory on, the first transfer is going to move data from this peripheral location to this peripheral location, to this memory location. And in the next transfer is going to move it to the next location, just like that. And if we have peripheral increment on and memory increment off, what's going to happen is that the first transfer is going to move data from this peripheral to this memory, and the next transfer is going to move data from this peripheral address to this memory. So effectively overriding what was there. And if we have both on for memory and the peripheral, the transfer is going to happen as such, moving data from this address to this address, and then increment the peripheral and increment the memory. So this address is going to move to this address, okay? Circular mode is basically a auto reload for the number of data transfer registers we have already talked about. So the transaction is going to continue happening as long as the DMA channel is enabled. As we have stated earlier in the video, memory-to-memory mode can be enabled through the code itself, so it doesn't need a peripheral request. And we can see here how the DMA can handle different sizes of data. So if you have a source that is different in size than the destination, this is how the DMA is going to deal with it. And as we have said, it does its data conversion through emulating. It doesn't provide true data conversion. So for example, if we have a source that is 16-bit and destination that is 18-bit wide, we can see here that the DMA is going to take the first portion of the lower portion of the source and move it into the destination, as we can see here. So the source content is going to be B1, B0, while the destination content is going to be only B0. So you have to be very careful when you are dealing with data sources and data destinations that are different in sizes. This is something that we also didn't state. Data sizes are usually byte or half word or a full word. Now let's get into how we can use the DMA in our projects. First, we will see how we can use it using the registers. Then we will see how we can use it using the ST-HAL provided abstraction layer. The first two registers are for handling interrupts. One is for the status of the interrupt, and the other one is for clearing the interrupt from your software. And we can see here that these bits are for the transfer, which one? Yeah, the transfer error. And this one is for half transfer, and this one is for a complete transfer. And then there is a fourth one for a global interrupt flag, as you can see here. The same also applies for the clear register. So when you are trying to use interrupts with DMA, there are two different registers, one for the status and one for clearing the register. So you cannot clear the flag from the status register and vice versa, for you cannot know the status of the flag using the clear register. The third register is the configuration register. Now there is 7 registers of these registers, one for each channel for DMA1 in this group of microcontrollers. And we can see here that the bit number 14 is for memory to memory mode. Then bit number 13 and 12 is for channel priority. Bit 11 and 10 is for the memory size. So whether it's byte or half word or a full word. The same thing is for peripheral size. The increment mode and the increment mode for both memory and peripheral, we have already talked about this. Circular mode as well. The fourth bit is for specifying the direction of the transfer to read from the peripheral or read from the memory. And 3 of these bits are for enabling the interrupt if you want the DMA to fire an interrupt in any of the events we have just talked about. And of course, the last bit is for enabling the channel. As you can see here, another address for specifying the number of transfers we want to happen inside a transaction. And this register can fill up to this number. And the last 2 registers are one for specifying the peripheral and another one for specifying the memory. And this is going to be all of the registers required to use the DMA. Now we can start writing some code. And the only piece of information we need from the reference manual at the moment is this section, the procedures of setting up a channel or configuring a channel. So we will go through all of these steps step by step. And the first thing I just want to talk about is the example that we are going to perform. Now, because I just want to isolate the idea of DMA in this video, I'm going to focus on a very simple memory to memory transfer. So we are going to be moving data from a buffer in our code to the memory address of the output data register of the GPIO pins. So it's going to be a very simple LED on example, not even a blinking example. No, it's just going to be turning a LED on. The first step is going to be setting your peripheral that you are going to use the DMA with in DMA mode. Now, GPIO doesn't have a DMA mode. So as I said, we will be performing a memory to memory transfer and starting the transaction from our code. To not make this video any longer, I'm not going to get into how to set up a GPIO pin using registers. I'm just going to use the STM32 Cube IDE generated functions. And this is just a function that initializes the GPIO pins that we are going to use. And as you can see here, I have configured these pins to be output just for this example. Okay, so now phase 2 or part 2 is to start setting up your DMA, and this is what we are going to do. And the first step when using any peripheral, you should first enable its AHP clock. As you can see here, it's stated clearly that before using a peripheral, you have to enable its clock in the RCC AHP enable register. And we could go and figure out the location of this register or the location of any other register we're going to use, but I think it's just too much bare metal. We are going to use the define files from ST. So basically we can just say RCC and get inside of this data structure and go to AHP enable register. Now, if we go to the reference manual again, and we search for the AHP enable register, we can see that the first bit is for enabling DMA1, which is what we are going to use. So we are going to be ORing whatever value inside of the HPNR with 1. And this is basically enabling the DMA clock. Now, I have to mention that this step is not mentioned in the procedure section, and it's not mentioned because the reference manual already mentioned this in a previous area, so no need to re-reference it again. And as I said before, when using registers, you could go and see its offset value and then figure out the location of the DMA in memory, or we could just use the ST provided define functions that has all of the values of these addresses for the family you are using already defined. So basically by using the DMA channel 1 define, we can go inside of this define and go down to the CPAR register. And now we can set the value of this register to be the data address or the data register of the peripheral we are going to use. And in this case, we are using GPIO A port. So we are going to use GPIO A port to define and then the data register of it. So we are going to write in GPIO A and then get inside of this define, and we can see that there is a ODR and a IDR register. Now, without getting into the specifics of general input and output pins, but ODR is for the output data register, and this is what we're going to use. And by doing this, we are accessing the value of this register. So what we need to do is we need to return the address of this register. So we're going to use this operator, and because this is a 16-bit register and this is a 32-bit register, we also need to cast it into a 32-bit unsigned integer. Second step is then doing the same but for the memory address. Now we need to define a memory location, and a memory location is simply a variable. So what we are going to do, we are simply going to define a variable. Now, for now, I'm going to be moving the data from a variable called LEDs into the data register of the GPIO A, and the value is going to be 4Fs, which means that all of the data register is going to be set to 1, which means that all of the pins on GPIO A is going to be set to high. And the same as this, we're going to use the same format. Here we go. And this is going to be the second step. Okay, on to step 3, which is setting the number of transfers. And in our case, we just want to move the data once. So we're going to perform one transfer inside of this transaction. And back to the reference manual, you can see that the register used to set this value or this configuration is DMA-CNDTR. And let's just set it for 1. On to step 4, which is setting the priority of the channel. Now the priority is inside the CR register, and it's offset to bits 2, 12, and 13. right here. And our channel priority, we are just going to set it to low, so double zeros. And first we will access the CCR, and just like that we access the CCR peripheral, and we're going to set this to 0, 0. But be careful, because if we do this, now we are setting the first 2 bits inside the CCR. So what we want to do is we want to shift these bits to this location. So we need to shift it from the 0th bit to the 12th bit. And we do this using the shift operator. And we're going to shift it to the left, of course. There is the right shift, just like that, but we're going to use a left shift, just like that. And let's just make it clean code. Okay, so the second thing we want to do is set up the rest of the configuration. So let's see what configurations we want to set. We have first the memory to memory mode. We need to set that to 1. Then we need to set the memory size and the peripheral size. We are not going to use circular mode, so we are not going to set this. And we need to set data transfer to 1 because we are reading from the memory. And we are not going to use any inputs with the DMA in this situation. And the last bit we need to set is the enable bit. So let's start first by going to the memory to memory mode and setting this up. So we want to set the 14th bit of the register to 1, and we are going to OR this, which means that any other value is not going to be replaced. And now we need to set the memory size and peripheral size. Now both of these will be set to 16 because the GPIO output data register is 16-bit. So we need to set both of these to 0 and 1, bit 8, 9, 10, and 11. So we're going to be left shifting it by 8 bits, then setting the data direction. And these are all the configurations we need. The final step is then start the DMA. And we're going to do this by changing the first bit inside the CCR peripheral to 1. And no conversion is needed. And we don't need to specify whether it's binary or not. And this is going to be it for the entire setup. So let's now connect a debugger to an STM32 and see how this code runs. And we will be taking a look at the registers for both GPIO-A and for DMA1. Now, remember that we are working with channel 1. So let's take it a step by step and see what will happen. So I'm going to first set a breakpoint right here. And let's resume until a breakpoint is reached. And let's take it a step by step. So this is the first instruction. Now we set the peripheral address. Step over. And let's go and check if the peripheral address is set correctly. As you can see, peripheral address is set correctly. If we go back to the reference manual and we see the register of the GPIO-A, the output data register of GPIO-A, we can see that it matches correctly. Number of transfers are also set correctly. Now let's swiftly go through the configurations. And if we go to the configuration register, we can see that circular mode is disabled, memory increment is disabled, as well as peripheral increment. The P size and M size are set correctly. Peripheral is set to low. Priority is set to low. Memory to memory is enabled. And all of configurations are correct. Now, for the last moment, when we start the channel or when we enable the channel. And as you can see, 4 of the LEDs are powered correctly. Okay, so we saw how we can use registers to configure the DMA. Now let's see how we can configure it very easily using ST-HAL library. So the way that most ST-HAL modules are set up is that you have a C struct that has a couple of fields that all represents the registers that we use to set up manually. Then you pass this C struct into an initialization function and then continue all of the operations on the module using functions defined by the library. This document is a description of STM32 HAL and low layer drivers, and I have navigated down to HAL DMA generic driver. And as you can see, there's a couple of fields that we need to set. And by the names of these fields, they are very similar to the ones we have already talked about. So we already know what the direction is, what's peripheral increment, and the rest of the fields. And this struct is called DMA init type define. The next struct is a handle struct. So it has an instance of the channel that we're going to use, and the init type define that we have already discovered right here. And the rest of the fields are not relevant to our application. These are steps to how we can use the driver. First, we enable the peripheral into DMA mode. GPIO doesn't have a DMA mode, so we are going to do normal initialization for the GPIO peripherals without any linking to the DMA. Then we set up the channel, or we basically set the fields of this C struct. But as usual, the documentation doesn't say that you have to enable the clock in the peripheral first. So we must first enable the RCC clock for the DMA using this function. And then we define a init type define. Then we set the rest of the configurations just how we did in the registers. So all of these configurations are the same as we did before. And now we have to define the handler, and per ST-HAL convention, we call it HDMA. Now, you may have a problem here because we have defined the handler inside a function, but it's inside the main function, so the program is not going to clear any variables inside of this function. But for the sake of correctness, you have to define anything like this in outside any function, so on a global scope. Then we need to set the instance, which is defined in the documentation as the register base address. And in our case, we are using DMA channel 1, which is actually a macro. And if we hover over, as you can see, it's a macro for this address. The last thing is to pass all of this information to a function called HAL DMA init, which is going to take all of this information and place it inside the registers of this channel, which is basically what we have done before doing this, but now it's much cleaner. The last thing we did when we were using the register was setting the first bit of the config register to 1, and the equivalent of this in ST-HAL is using a function called HAL DMA start. And if you didn't take notice, till this point, we haven't set or specified either the peripheral address or the memory address, because this is going to be performed also in the DMA start function. And this is basically it. And if we run this code, we will see the same results. Okay, and this is going to be it for this video. All of the stuff I didn't talk about in this part, I'm going to talk about it in part 2. So we will be doing the same as we did for digging inside the reference manual and stuff for STM32F4 family, as well as we will discuss interrupts in DMA and hopefully give a more advanced example than the one we gave in this video. I try to provide as much value as I can in my videos, so consider subscribing. Leaving a like is always appreciated, and thanks so much for watching.